Hello everyone, I'm Mukul and I'm here today with my friend Rakesh, and we'll be presenting Apache Ozone, and we'll be talking about how did we support multi-protocol access in Ozone. So let's start with the quick agenda. So we'll be talking about Ozone architecture, the various ways of using it, using the interfaces. Then we'll present the unified design, the use cases which we normally expect against Ozone, and a couple of features which came out of this. Let's quickly go into the architecture. Before I start, Ozone is a distributed object store which we have developed, and it currently scales up to tens of billions of objects. And Ozone had been developed to overcome the scalability limits of HDFS. And the architecture derives a lot from the current HDFS architecture. So on the top, we have the Ozone Manager. Ozone Manager is our namespace utility. So it keeps the file path to block mapping. Right below this, we have the Storage Container Manager. And the Storage Container Manager ensures that each copy of the data is sufficiently replicated. It also manages the data node lifecycle. So things like decommissioning and other things are managed by Storage Container Manager. On the right, we have the Recon Server. The Recon Server is the administrative utility inside Ozone, and it listens to information from the Ozone Manager, Storage Container Manager, and the data nodes, and gives insightful information about the data which is written. And at the bottom, we have the data nodes. These are very similar to HDFS data nodes, and this is the place where the actual data is stored. On the left, we have got the interfaces using which people can talk to Ozone. On the top, we have the Ozone file system connector, which is the Hadoop compatible file system. This is very similar to HDFS, like file system or the distributed file system. Below this, we have the CLI shell. The CLI shell was developed to help developers with in testing out the Ozone cluster, but this is completely feature rich and it provides an additional access mechanism. And below this, we have the REST endpoint access using the S3 gateway. And here we support the Amazon S3 protocol. Using this, the data can be written using the Amazon S3 protocol to Ozone. Let's now go a little bit further into the Ozone interfaces. So on the right, we have got different kind of compute frameworks which are there, which are Hive, Spark, and Flink. And they can interact with Ozone using either the OFS protocol, which is our Hadoop compatible file system, or right below we have the S3 protocol. Hive and Spark can talk to Ozone using the S3 file system. We also support what we call as HDFS like URI, and this is done using the Vue HDFS protocol. And Vue HDFS supports mount table, using which users can define mount table and access Ozone. And then all the other access patterns which we have got are all S3 related. Let's start on the left where we have got the S3 ingestion. And here we support the Python Boto3 library, using which and the AWS S3 CLI and the S3 command, which are the HTTP command, using which users can talk to Ozone. On the top, we have the S3 browser, which is supported on top of our Ozone gateways. And then we have the Kubernetes containers, which can talk to Ozone using an S3 compatible file system, which is called Goofies. Now, before we go ahead, let's talk about use cases which we expect to run against Ozone. The first use case which we have got is called is the pure S3 object store workload, where we expect users to use Ozone as a pure S3 like object store, and all the objects here would be key values in terms of key values. The other real workload which we see is the one where customers are trying to use Ozone to replace their current HDFS clusters with Ozone to fix their scalability issues. Right below this, we have our multi-protocol access use case, where we expect users to write in data using, let's say, the Amazon S3 protocol and read via the Hadoop compatible file system, or vice versa. And this really provides a mechanism where customers should be able to use it in any ways. We have always designed Ozone to be extensible, and we also feel that we would be able to extend Ozone to support protocols like NFS or CSI level integration later on. Okay. So let's quickly bring it all together really fast. So we have these Hadoop compute applications like Hive, Spark, Impala in blue, and they all talk to the storage using the Hadoop compatible file system API, which provides a standard connection mechanism. And in any of the modern data center, we would see uh, something like HDFS, which has been around for some time. Ozone is also there as we are proposing it right now, which is done using the OFS protocol. Then we would always have some kind of cloud access, which is done using either the WASP connector or the S3A connector. And Amazon S3, as in terms of its own protocol, is now also widely prevalent in on-premise storage. And so some of the more commonly known open source S3 S3 compatible object stores are Apache Ozone, Ceph, and Minayo. And these compute application can also talk to the S3 compatible object store using the S3 connector. We have also mentioned CSI in here because CSI is also really important storage access pattern in the CNCF world. And Ozone tries to provide CSI compliance using the GoFees protocol. Now, we'll go ahead and share more details about how do we provide multi-protocol access. And Rakesh should be taking further on this. Over to you, Rakesh.
Hey, thank you, Mukul, for setting the tone and providing the overview and the introduction slides. And I'll be taking through the Apache Ozone internals where we achieved, we'll show how we have achieved storing both files and objects into a single Ozone cluster. And the work is already finished and it is uploaded to the Apache master branch. Okay, now if you look at this case, a single unified design represents both files, directories, objects, and buckets. So we'll see how it looks like. And the bottom side, you can see a data in place and how do we provide a view, a hierarchical namespace view, which comprises of directories, subdirectories, and a bunch of files underneath. And here we are maintaining a parent-child relationship, right? And on the right-hand side, you can see a flat object store namespace. It's a key value store. So here we could see that we are maintaining a complete key absolute path like directory 1/directory 2/3/file1, and the bunch of files we'll be keeping in this fashion. And there is one common pattern we could see is like the prefix path, right? Directory 1, directory 2, 3, which is duplicated all over these bunch of files or the keys. Yeah, so we look at about the HCFS use cases and type of workloads which are running on top of the object store thing or the file system. If you look at the Apache Hive, Impala, or the batch of operations like the Apache Spark or typical traditional MapReduce job, all these have common similarities or some similarities. Like all these expects a strong consistency without any partial results in case of any client failure or network failures, packet loss. And when they are doing a rename or delete operations, it should be consistent. And when user is performing a recursive directory deletion or moving content from one directory to another directory, all these operations should be consistent. And when I'm dropping a table, a high table or a managed Impala table, it should complete in a deterministic time frame. Same to the job committers. So the performance of the job committers are directly impacted due to the rename operations of the temporary output files to the final output location. So when you run batch operations of Apache Hive, Impala, Spark, they often generate a lot of temporary output files, and all these will get renamed at the end of the job using the job committers, and it involves rename operation. So the operation is directly proportional to the way how quickly we are completing the rename operations. Yeah, we'll see some of the design considerations. When you look at the hierarchical file namespace, it has intermediate directories in place, similar to the HDFS. Also, these batch operations, big data tools, they expect atomic rename and delete operations. Also, it expects deterministic performance numbers. Of course, when you are bringing a new storage system in place, it will get compared against with the HDFS. So more or less, it has to achieve the same performance numbers with the storage system versus HDFS. And the another interesting fact is like interoperability of the same data. When you have a data in place and there are various protocols like Mukul mentioned in the previous slide, like S3, AWS S3 client and the HCFS compatible file system. All these things will get access to the same data and will try different various workloads. So we'll see more into the coming slides. Okay, if you look at the architectural point of view, we have carefully taken a decision, architectural decision, design decision to bring a new element into the system, new attribute into our Ozone cluster, like Ozone bucket types. A new attribute we have added to the existing buckets. Since we have already volume and bucket in place, it was easy to add a new attribute to the system. And using it is based on the various use cases. We have categorized buckets into various use cases, like file system optimized bucket, which provides 100% file system semantics. Also, it provides same hierarchical view similar to the HDFS, and we are providing capabilities, additional capabilities to make use of the file system optimized to read and write using Amazon S3 protocols. And next is like object store. Object store provides a file system, a flat namespace key value similar to the Amazon S3, and we are adding one more bucket type is like legacy, which is basically to provide upgradation, smooth upgradation. Let's say you have a cluster in place and which is running an older version, and I'm upgrading the version, the Ozone version to a new thing. So what will happen to the old buckets, pre-created buckets? All those things will get represented as legacy, and it can be accessible to the new clients or the new versions. Yeah, and this is how the client, the bucket type is completely owned by the client or operated by the client, not owned, basically operated by the client. The client can, while creating a bucket, client can specify what is the type of bucket, whether it can be FSO or it can be OBS or it can be legacy buckets, and all these can be coexisted in the single Ozone manager. And we have a bucket table in place, which is backed up with the RocksDB. And this is how you can create a bucket. We have provided a new attribute layout to the Ozone shell command so that admins or the users can create Ozone buckets using these attributes, and all these buckets will get created accordingly. Yeah, now from the Ozone manager perspective, when client is performing any operation, they'll be doing operations on keys and keys which are residing under a bucket. In the Ozone manager, what we have done is like we have added an intelligence, a bucket specific intelligence to the Ozone manager, so that Ozone manager will handle those client requests and it will execute in a separate, completely isolated execution path. Now the client or the customers, they can operate on various buckets. For example, some applications, they would run file system kind of operations, batch operations. They can create a bucket and they can put all those file content into those file system optimized fashion and perform. Similarly, AWS S3 client, they can create OBS bucket, and admin has to create OBS and give to the AWS S3 client, and they can operate on the OBS buckets, and they can put keys into the Ozone. Similarly, the legacy for the upgradation path. So now with these in place, Ozone manager has intelligence to handle all these operations, and it has provided the complete isolation across workloads. Now we'll see about the Ozone file system optimizations. We'll look at the file system optimized capabilities. It helps to provide an easy migration of workload from HDFS to Ozone without any significant performance degradation. How we achieved is through the rename and delete operation, which irrespective of the underlying subtrees or subpaths, how big the subtrees and subpaths, it completed the operation in order of one complexity. Yeah, now we'll see more into the internals of Ozone Manager, how the files and objects are organized into the Ozone Manager. So when a client is creating a key, we have a key table in place. If the bucket type is object store, we will be maintaining a flat namespace like this, volume, bucket, directories, and then keys. So these will get added into the key table. There is a dedicated key table for that, which is backed up with RocksDB. And the file system optimized, we have clearly separate tables maintained, splitted the key table into two things, directory table and file tables. And here the prefix ID is nothing but basically the parent ID to maintain the parent-child relationship. And we have a bunch of directories like directory 1, 2, 3. Directory 1 has a relationship with bucket ID, which is 512, for example, and which has an object ID created when I'm creating a directory. It produce an object ID. We are making use of the transaction IDs, so it will maintain uniqueness across the operations. And once the directory 1 is created, we'll be creating directory 2 using the object ID of directory 1. And it continues the same fashion. Multiple directories can coexist. And again, the file table, when you look at the file table has a relationship to the directory table, and which uses the prefix IDs of the directory table to provide the parent-child relationship. And this is how we are organizing the objects and files in the Ozone. Now, when we look at the interoperability of the data, so when we say the bucket type laid down a path to add more sophisticated features to the Ozone, and we are adding more enhancement and feature richness to the Ozone on top of the bucket type element. Interoperability of the data is one of the piece. So here user can ingest data. On the left-hand side, you can see AWS S3 client, which ingests the data to the Ozone, and the S3 gateway is the endpoint. And here we'll be writing the data to the Ozone cluster. And then on the right-hand side, you can see the Ozone file system client, OFS client, which is an HCFS compatible file client. Using that, we perform the read operations. And here we can place all your batch operations. Like you can perform the Apache Hive queries, Impala queries, Spark jobs, or traditional MapReduce jobs. Also, it can be reversed. The data ingestion can be through, for example, a batch operation has been performed, and the output I would like to add into the Ozone cluster using that. And on the right-hand side, you can place AWS S3 client to perform those kind of applications. So one capability we are bringing is like the data is in the Ozone cluster, and using the same data, you can access through various protocols. So you no need to worry about copying the data from one cluster to other cluster, and specifically for your workload. The same data can be accessed using different protocols. Yeah, we'll see some more details. And earlier we saw the directory table and file table. So here, the S3 client, when you write using the S3 client, user or admin has to create a specific bucket, a file system optimized bucket. And I just made a FSO bucket. It can be any name, any valid bucket name. Now all this bucket will be stored in the bucket table, and the keys you can write, and the directory table and file table will maintain the namespace. And there is one additional thing is like range actors. When user is performing operations, of course, the permission is one of the criteria, right? One of the concerns. So the permission part, we have added intelligence to the ranger ACLs, so that ranger ACLs can be performed within a millisecond or a microsecond operations. In-memory operations, it can do by accessing the directory table and file table content and complete the permission checks. Yeah, and we have a bunch of items in our pipeline for the future enhancements. And one of the things is like directory caching. when you look at the file system optimized, that it maintains a top-down traversal. Parent, you have to traverse from the parent to the child. So it has to traverse across all these intermediate directories. And one thing we are experimenting, or we in our basically we are planning or we are proposing, is like directory caching mechanism. Either it can be routes DB off heap cache capabilities, or it can be a dedicated on heap directory caching. So those things we are under discussing, we are designing. And another thing is like similar to HDFS, there is a global lock in place in Ozone, which is a bucket lock. And for any operations, user has to user will, when the user is performing any operations, it goes through the global bucket lock. And we are planning to leverage the bucket type capabilities and bringing out the enhancement to manage the lock. Instead of maintaining the bucket lock, key path lock can be leveraged to reduce the lock contention. And those are under production and under designing, and we will be providing the capabilities on top of OBS and FSO buckets. Another thing is like data replication across clusters. So you can manage your data replication for OBS and FSO buckets, and those are under implementation. And we have a bunch of contributors. They have contributed continuously to these features, and I would like to thank all of them. And also I would like to thank the community, Ozone community. We have a very vibrant and dynamic community, and I would like to thank all of those members. Please feel free to reach out to these mails if you have any queries, or if you would like to contribute more into the Ozone, please do so. Welcome all contributions. Thank you. Thanks everyone.
Thanks everyone for joining this. Thank you.